All right, I guess I'll get started. I guess it's just the virtual people. So today I will be talking about the new burst patches within BlastFOAM. So we hope to have it released by now. Unfortunately, it wasn't. However, if you are interested, I have pushed it to the development branch on our GitHub page if anyone wants to play around with it. Mostly just for this, since it is the topic of a workshop. Okay, so basically just going to go through a little bit of background on the company, BlastFOAM, governing equations, that kind of stuff. Talk about some basic detonation models, and then we'll get into the meshing, which will be the main part of this. So block mesh, snappy hex mesh, and then really how to use topo set to create baffles, and in this case, the burst patches. And then a little bit on the use of set refined fields for setting the charge, and then running and looking at some results. So background on us. So BlastFOAM was developed by Synthetic Applied Technologies. We started in 2017. We are based out of the Capital Factory in Austin, where we're kind of intermixed with a bunch of government clients as well as other integrators. And really what we do is we develop and maintain software platforms. Relating to BlastFOAM, we have BlastFOAM, Citicore, and iBallistics. Citicore and iBallistics use BlastFOAM as a base to do insurance type modeling or propellant design, that kind of stuff. And then really we work with commercial and federal clients and do a lot of applied research projects. And then currently we're partnered with the University of South Dakota HPC for all of our HPC needs. So I'm Jeff Heilman. I have my PhD in mechanical engineering from Iowa State. I have been the lead developer of the BlastFOAM CFD solver. Really, my background is in OpenFOAM. I had done incompressible multi-phase flows for my graduate work. And then since then, I've moved on to compressible and still multi-phase flows. Next, we have Ben, who does a lot of our application, so specifically insurance modeling. Then we have Peter Vonk, who did the original implementation of BlastFOAM way back when it was just starting. And he leads a lot of the R&D efforts and that kind of stuff. And then lastly, we have Tim Brewer, who was a technical Army officer for approximately 18 years of experience in modeling and simulation. And then he is our PE and does a lot of the really cool simulations that you'll see on LinkedIn if you follow us at all. So then just some quick examples of kind of like where BlastFOAM is used. So looking at loads on different structures. So top left, you can see like an aircraft, particle and dust entrainment. We have some multi-point detonation. The cityscape and urban terrain is one of our big ones, where we're basically looking at loads and damages on buildings that are generated from these blasts. We've done a little bit with nuclear weapon effects, debris, fragmentation, Taylor-Richtmeyer stability is kind of looking at more of like a DNS type, not exactly, but more along those lines. And then undex, and then structural responses. And then here's just quick video examples. So there's that Taylor-Richtmeyer instabilities where you can see the density gradients. Have our geometries on more complex geometries. Next, we did some work. This was a very large case. I think it was 12 tons detonated in a field. Basically, they were looking at the structural response of this structure in particular due to the loads. So we ran these calculations and we sent them to another team who actually did the structural response using the loads. And then this is a typical cityscape detonation that we use to estimate damage, that kind of stuff. Okay, so BlastFOAM, really the reason behind this was within this industry, the BLAST specifically. There are not really any unrestricted or open source codes that you can use. And what is there is typically they're very expensive and very restrictive. So we were looking for something that could be used by really everyone, that you could easily validate. You could validate it yourself. You didn't have to take someone's word for it. So for those reasons, this is based on OpenFOAM, obviously. Huge library. You get a ton of great stuff out of the box: mesh generation, parallel, pre and post processing utilities, and really it just gives you a great balance of usability, scalability, performance, and it's really just a solid base to build off of, which is exactly what we've used it for. There's also a lot of things in there like turbulence models, chemistry, all of that, which could be again used without having to duplicate the work. Okay, so just a quick roadmap. So as far as where BlastFOAM started, where it's been, so it was originally presented in 2016, 2017 at the OpenFOAM Users Conference. Since then, we've gone through quite a few iterations, the first public release being in November 2019. Since then, we've added a lot: thermodynamics, radiation, incorporation of adaptive mesh refinement from Myers 2019. So this included 2D axisymmetric, as well as load balancing. Done a lot of work with more true Euler multi-fluid, multi-phase models. We added support for Lagrangian. And then, so the upcoming release, which should be out in August, really is going to have a focus on a couple different things. So we'll have support for solids for foam, both in direct coupling to it, and then also we have a modified version, which will be, you don't need the external library for that. But both options will be there. There is a new or heavily modified numerics library, which will include bunch of basic numerical methods, numerical integration, root finding, optimization, that kind of stuff. We'll have ported from Foam Extend is polyhedral refinement, with the addition of support for load balancing, as well as axisymmetric cases, at least in 2D. And then lastly, burst patches, which is what this workshop will be talking about. All right, so just quickly over the governing equations. So here we're doing a two-phase simulation. So this is more along the lines of like a VOF type approach, where you have two compressible phases. So we track a volume fraction of one of these phases, and then we'll track phase mass for both, and then we have momentum and total energy. So to do this, we have our conservative variables, so volume fraction, masses, momentum, and energy, and then we have our fluxes, which end up being basically the same as the Euler equations, aside from the fact that you have split your mass into two parts. You also have volume fraction. We also have a source term. So for the volume fraction transport, we have this additional term, which is due to the fact that alpha is a non-conservative variable, so it's not conservative when you transport it. And then we also have this energy source term, which is basically how energy is added to the domain when you have these detonation events. Okay, so the basic detonation problem is we have some solid reactants that will be transitioning to gaseous products, and these are going to be expanding into air, which we'll be treating as an ideal gas. So typically, we assume that this detonation event happens at a single point in space, and then we have a reaction that propagates outward at a prescribed detonation velocity, or according to some model. It's actually very easy to find these detonation velocities for most high explosive materials. Generally, if you can find coefficients for the JWL, which I'll talk about in a second, you'll always have the detonation velocities. So the reaction zone, basically that area between the products and reactants, is generally very, very small. And we can assume basically infinitely fast reaction kinetics. And really, the reason we do this is just because it ends up being on the order, it's sub-millimeter, which is generally speaking far too small to measure for the types of simulations that we do. So more large-scale engineering. And really, it doesn't add anything to look at these kind of effects, and yeah, it doesn't end up having any effect. Even some of the more complicated activation models don't change the results. So the reactants it's the unreacted explosive material. It's generally a solid, and basically we care about how this transition to the detonation product. So it's represented by a unique equation of state, meaning you can use variable equations of state to do this. And basically we have some blending. So we have this PJWL, which would be the products, and then we have the solid pressure, and we have lambda here, which is basically reaction progress variable. So 0 is basically solid, unreacted. 1 would be gas and fully reacted. For the product gases, we tend to use the Jones-Wilkins-Lee equation of state, or the JWL equation of state. It's very well established for energetic materials, and again, is extremely easy to find the coefficients for, surprisingly. But as you can see, it's pretty complicated. So we need omega, R1, R2, A, and B. And basically, we end up using a reference density as well to get this B term. Yeah, where the reference density will be that of the solid. Lastly, we have the air phase, which for here, we're going to be treating it as an ideal gas. However, it doesn't have to be. This could be some stiffened equation of state for water or some other equation of state. But for this case, we'll be treating it like an ideal gas. So the detonation model, I mentioned you start at a point and you use some model to say how that spreads from that point. So really what this does is it tells us how to release energy into the surrounding material. So we have a couple different transition models or activation models. So none, basically all of the energy is released as soon as you start the simulation. The linear, which uses that detonation velocity, will start from a point or points and then propagate outwards at that velocity and react as it passes. Then we have pressure-based, which basically uses compressive as well as pressure, kind of a power law rule to determine the reaction rate and release energy that way. Have Arrhenius rate, which is temperature-based rather than pressure, and then programmed ignition, which has compressive as well as a linear part. So it's compressive and linear detonation. And then we also have additional models for afterburn, which is basically when you have, they're typically used for internal detonations where you're detonating inside a closed vessel and basically you have secondary reactions that occur and release additional energy. So we have Miller, which is very similar to the pressure-based. And then we have a linear release, which basically releases some amount of energy over a given time. So for all of these, we have our reaction progress variable lambda, and basically we blend all of our thermodynamic quantities. So different than a multi-species approach where you actually blend the coefficients, here we actually blend the outputs of those equations of state, whether that be pressure or speed of sound or temperature. And that's just because we have different equations of states and you can't blend them. So M here is typically going to be 1. It's just that power of lambda. And lambda is, as I said, the reaction progress variable, and we evolve it based on this equation. So we have a conservative transport with some reaction rate, where R dot is determined by whichever model you choose. So for the linear model, basically when that wave passes through a cell, you get some non-zero reaction rate. But before and after that, it's 0. For pressure-based, that rate is determined by the equations. And then none, it all happens at the very first time step. So after we have this R dot, we basically calculate the energy that is added to those governing equations, which is just going to be E naught, or the detonation energy, generally given in terms of the pressure divided by the reference density, and that's multiplied by the time rate of change of the reaction progress variable. In Afterburn, we'll use these exact same equations. However, you'll have a different R dot and a different energy. So both of these states, the unreacted and reacted, are defined by some thermodynamic model. So here, these are just going to be the equations of state. For the reactants, we like to use a solid equation of state. So Murnaghan, Birch-Murnaghan, either second or third order, solid JWL or the Cochran-Shan. And then for the products, we have the JWL, JWLC, which has some extra term, and then LSCK. And then similar to the OpenFOAM thermodynamic models, you can also compile additional options at runtime. And then the the required activation model and the optional Afterburn model. Okay, so then now to the burst patches. So the burst patches, basically, they act as a patch before some condition is met, and then after that condition is met, they quote unquote burst, and flow is allowed to go through that patch, or the patch type changes. So slightly different than the pressure activated baffle, which uses the cyclic ACMI patches. You only need one patch per side, so you don't have to define multiple patches. You don't have to define a cyclic patch and a wall patch. It's only one, and then it transitions. So the main benefit of this is that you can use it with adaptive mesh refinement. The cyclic ACMI patches tend to give problems because you're trying to just the way the refinement's done, that can cause it to break, just because it doesn't really know how to do certain things. So these burst conditions, which basically tell you when that phase transitions. Right now, we just have pressure, impulse, and pressure and impulse, where if you're going to use impulse, you have to have basically an impulse field stored. The easiest way to do this is with the function object. But again, this is a runtime selection table, so if you have some other condition, it's pretty easy to add. And then once this burst condition is met, there's two options as how to handle that. So either all patches on the face burst, which is full, or individual faces can burst, meaning partial. And then it's called intact. The intact field will be written so you can view it for post-processing. And basically using the threshold filter in pair view will allow you to see open faces, which is nice. So then we also have the option to, as far as how to calculate the value, I guess, or the delta across the faces. So you can either use the delta, which is going to be the value on one side minus the value on the other, or you can just use the maximum value. I'll talk about why in a second. And then, so the three patches that we currently have, so burst, which is basically a non-coupled boundary, so you go from having a wall to having an outlet. Burst cyclic, which is just a cyclic patch. It really shouldn't be used with adaptive mesh refinement, just because it can cause some mismatch between the two sides. And then burst cyclic AMI, which uses the AMI interface. Just a quick example. So on the top, we have three windows or bursting patches, if you will. This uses that partial burst. So you can see, and this actually uses both a pressure and an impulse. So the first two faces or patches burst due to overpressure, where the third, you can see it kind of lags a little bit. And that is because when it does burst, it's because of impulse, not because of overpressure. And then the bottom is just nothing. So you can see the difference. And this is the internal detonation with obstacle and glass tutorial. Okay, so then this will be the bursting window workshop tutorial case. Again, all of these are in the development branch. So the case description here, we're going to be using 25 kilograms of C4 with a 1 meter standoff and a detonated from 1 meter above the ground. The building, it's really just a room with a window. We'll have an empty interior, and we're going to do a symmetric case, so symmetric in the Y direction. We have glass, or the burst patch, which separates the charge from the inside of the building. We're going to be using a burst pressure of 5 E/6 pascals. We'll be using partial breakage, and then we're not going to be using the pressure differential. So basically, we're just going to be taking the maximum value of either side. This is mostly just because you can have unloading and loading, which causes kind of a checkerboarding effect. So we just went without it for this. So the required files, these are basically all the same as you would use for either a standard BlastFOAM case or really a standard OpenFOAM case as well. So you have your initial conditions, you have pressure, densities of air in C4, temperature, volume fraction of C4. For constant, you have phase properties and dynamic mesh dicts, which is only required if you're going to be using adaptive mesh refinement or some mesh motion. And then in the system files, again, all the standards except the main difference would be topo set and create baffles dict. So here is just an example, or not an example. This will be the building that we'll be meshing, just the STL. So for our block mesh, we're basically just going to be creating a domain. So -5 behind the charge and 10 meters ahead of it. We will have a 10 meter in the Y direction, 10 meter in the Z direction, so 10 meter height. And then we're going to have a ground, an outlet, and a symmetry patch. So here's just the block mesh created from that, where we have the ground, symmetry plane, and then our 4 outlet faces. For Snappy, so we're basically we just want to remove that building. This has been set up so it aligns exactly with the STL file, the mesh edges, or the cells, sorry. So we're going to be importing our building to that STL file, 9 millimeters, so we're scaling it. And then basically we're just going to be refining and cutting. So we don't have any snapping in this because it's a block and it's lined up with the mesh. But we will be using level 2 refinement just so we keep those, mostly just so we keep our edges aligned. So here is our mesh created with Snappy Hex Mesh. The green will be that new building. You can see the refinement around the edges. So once we've created our mesh, we have our building cut out of the mesh and refined. We need to create our baffles. So to do that, we have to create face zones. You can also use patches. We'll be using face zones. So to do that, we use topo set. So within topo set dict, we want to create a new face zone. It's called face zone set here. So this is going to be a new set, and we're going to be using a searchable surface to face zone. So because this box, the searchable box here will basically intersect the center of the walls, it won't actually select any faces except for that window face. You can also use a plate here. A plane would not work just because you go higher, but a plate or the searchable box would work. So after we run topo set, these green faces here are selected. So these are added to that face zone set. One note, so it does have to be a face zone just because you need to have some directional information so it can decide how to, or which owner and neighbor face to select for the actual patches. But these are our selected faces. These are the ones that will be added to the baffles. So next, we actually create the baffles. To do that, we use the create baffles utility, and we specify this in create baffles dict. So we're going to be using a face zone. The name of that zone is Windows, which was specified in topo set, and this will be a Windows baffle. So the way that this works is it specifies Windows _ master, Windows _ slave as the two patches that it will be creating. You can actually specify these as well, but using the patch pairs here, we'll just create those master slave versions. So we're going to be using the burst cyclic AMI patch, just because we're going to be using adaptive mesh refinement. And then we're going to be using the pressure burst model. So basically looking at the maximum pressure on either side to see if it bursts. We will be using partial burst, so basically allowing fragmentation through that window. And then we will not be using the deltas. Okay, so to actually create this mesh, we run surface features to extract that information from the STL file. We run block mesh to get our base mesh. This will be run in parallel, so we decompose it with the copy 0 flag, basically making sure that we keep all of our empty patches. Or all of our patches which are not there, I should say. Then we run snappy hex mesh with the overwrite flag. We create our face zones for the windows using topo set, and then we create the burst patches using the create baffles. So the final mesh here, we have the ground, which will be a wall patch. The orange here will be that you can see, the side you can see will be the Windows slave, the back side will be Windows master, and then the green is the building. Okay, so setting the charge. So here we're going to be using set refine fields, which is really just a variation of the set fields utility from OpenFOAM. There have been some notable modifications, especially in this next release. So the way that set refine fields works is it'll set a value, it'll refine the mesh, and then it'll reset the value until there's no cells that are refined. So it refines either based on the fields that you give it here. So alpha.c4, basically when you have some variation in that, it refines. Or you can specify this refine internal keyword, which will tell it to basically refine all of the cells within the volumes that you give it. In addition, we also have some other options. So rather than just the vol scalar field value, you also have some things like initial value, which will keep not old non-uniform fields which are read in. Sum, which is nice for volume fractions. You can do 1 minus the sum of fields. Mass integrated function, which is you can use function 3, which are in BlastFOAM. Again, really just variations of function and function 2. Yeah, just some more things you can do, and really to set non-uniform fields without having to use the coded entries. So we're going to be setting a region. This is a BlastFOAM specific one, so a spherical mass to cell. Basically, we're going to be setting with a center of 001, a mass of 25 kilograms, and then you have to give it a density. So this backup section here, this is basically if no cells are selected due to the radius or whatever volume you give it, if no cells are selected, you use this backup region. And this is only used to refine cells. It's nothing is actually set there. You'll get warnings if nothing is set. But this will basically allow you to refine, catch additional cells, and then try and set the true values again. So again, refine internal refines all of the cells within the volume. You can specify the level of refinement which you want, and then the field values. So alpha.c4, we're going to be setting to 1. The default field value here is actually very important, just because when you restart the loop, after you've refined, you want to reset that value to whatever the background value is. So that way you're not just setting over top of your old value. So this will be our initial charge. So again, we're 1 meter off the ground, 1 meter away from the front of the building. And this has just been mirrored. That's why it's a sphere. Otherwise, it would be just half. Okay, so running the case. So really, this file is just meant to illustrate how to use or how to set the boundaries within the files, within your initial conditions, sorry. So for the building and the ground, they're just walls. We're going to be using a slip boundary condition for velocity. So the main patches of interest here will be the Windows master and slave. So here we're going to be using the burst cyclic AMI patch. And with these, you have to specify an intact patch type. So basically, this is the patch type before you actually burst. So to do that, we just give this intact patch dictionary and this type slip. So this, again, you can select any patch type, fixed value, zero gradient, whatever you want. And it'll use that before burst. And then, yeah. And then because we're using the copy 0, we do have to have this processor, which basically just specifies for the constraint processor, use the processor boundary. Next, we have the phase properties file, which is kind of a combination of the multi-phase phase properties within standard OpenFOAM and the thermophysical properties. So here we have 2 phases. We'll have air and C4. C4 will be detonating. And we will have 2 entries here. So we'll have reactants and products. So the reactants will be the solid equation of state. Won't really be important at all here. I'll talk about that in a second. But we specify our molecular weight, equation of state, transport, and thermodynamic quantities. And then we have our products. So this will be using the JWL equation of state. We're going to be using an E polynomial thermo model. So this just gives a little bit more accurate temperature. It's just linear. And then equation of state, again, these are pretty easily found for C4. These are the JWL coefficients. We're going to be doing an InvestGrid simulation. And then, as I said, linear for thermodynamics. So we are not actually going to be using an activation model. This will just be basically when the simulation started, all of the energy is released, and then it goes on. So for that reason, you don't actually spend any time in that solid state. So it's not super important to have it. But we do have to specify our detonation energy, which tells you how much energy to add. And then lastly, we have our air, which basically is just the surrounding. It's going to be an ideal gas with a specific heat ratio of 1.4. Next, we have our function objects. So basically, these are just some additional things, more illustrative than anything. So if we did want to use that impulse burst condition, you just have to add the impulse function object and give it some reference pressure. So here we're going to be using a little over 1 atmosphere. Same with overpressure. So the store flag basically just says, do you want to add it to the database so you can use it not just when you're writing it, but for other things. So we do for this because we actually want to probe it. And then, so lastly here we have our pressure probes, which will be of type blast probes. So this is a variation of the standard probes utility, really just some quality of life additions. So we have this adjust locations flag, which basically says, do you want to adjust this probe if it's outside of the mesh? So if it is outside of the mesh, it'll just move it to the closest cell. It's nice if you're barely off or you have some weird STL geometry or your mesh doesn't quite align with your STL. It'll allow you to not fail and not write bad values, but move them inside the mesh. We also have this append flag, which will, if you restart a simulation, it'll just continue that log file. It'll overwrite values after you start, but it'll use the same file as opposed to starting new files, which then you have to concatenate. And we're going to be, again, Same as the standard probes. So we're going to be probing the overpressure and impulse, and then we have our locations. Next, we have the dynamic mesh stick. So we're going to be using the adaptive FE mesh, which basically has access to all of the dynamic load balancing, 2D, 3D, 2D axisymmetric, all of the refinement methods. We're going to be using the density gradient, which is basically a normalized and modified density gradient. Refining every 3 steps with our upper and lower refinement intervals or levels, sorry. These are kind of case specific. 0.1 seems to be pretty good for the density gradient as far as giving decent refinement, but also unrefining fairly quickly, so you don't refine everything. But again, it's kind of more of an art to get good values if you want to really control that tolerance. The number of buffer layers here is slightly different than the standard OpenFOAM refinement method. So rather than specifying levels which are not refined, this actually refines extra cells in front of for here it'd be shock front. So it'll give you that refined buffer layer. And we're only going to be refining up to level 1. And then dump level just writes the cell level as a vol scalar field and point level as a point scalar field. So for the FE schemes, we're going to be using the Tadmor scheme. So this is in row central foam. There's Kurganov and Tadmor. These two seem to work best for spherical detonations. Basically, they don't result in any sort of numerical artifacts, which you can see with some of like HLC or HLL, any of those, I'd say more standard flux schemes or Riemann solvers, they tend to introduce some artifacts, or at low speeds, which we do tend to hit after some time. You can get some checkerboarding and some other weird effects, which the Kurganov and Tadmor schemes do not see. We have our time integrator, which is basically our Runge-Kutta method. So we have a bunch of options for this. So the RK2 method is just a second order strong stability preserving Runge-Kutta method. We also have options for 3 and 4 step variations, which basically just allow for additional stability. So still don't recommend going above a current number of 0.1. But if you have, especially for detonation problems or other, I'd say harder problems, you can accidentally go over that 1 for a time step or 2. In some cases, that will cause you to fail almost immediately. However, with the higher order or the higher step variations, it will make that much smoother and you won't fail. At least you're less likely to. The grad schemes, so cell MD limited is actually incredibly important. Some cases, if you just do like a least squares or Gauss linear, it'll fail almost immediately, but switching to that limited gradient you have 0 problems. Incredibly beneficial. For the divergent schemes, for basically all of them, we use the flux schemes. The only difference would be for the advection of lambda or the reaction progress variable. So since this doesn't have direct access to the flux scheme, this Riemann divergent scheme basically will look up the flux scheme, interpolate using whatever the flux scheme uses to interpolate, and then calculate the flux that way. So for something like HLC, which has wave speeds, those wave speeds are stored, and then lambda is interpolated using those. And then lastly here, we have our interpolation schemes. So reconstruct variable name will basically tell you how either the limiter or the reconstruction method, so like Musil. We have our quadratic Musil. You can use, here we're just specifying our limiter, so Van Albada, min mod, etc. Yeah. Okay, so then just some quick results. So here we have our pressure contours. So half of this is obviously pressure contours, half of it is not, so you can see it. The building has kind of been cut away. So we'll zoom in a second on the glass so you can actually see what's happening, but you can see that those pressure waves get into the building, especially at the start. It only goes through a section of that glass. Okay. So next we have, so this is a zoomed in front view of that window. So you can see it breaks as that pressure wave goes out, and then as it reaches basically that 5e to the 6 pascals, it stops breaking the window. You can see along the edges, it continues to break, and that's just because of the reflections of the pressure. It keeps that pressure higher for quite a bit longer, so you still get breakage around the edges. Okay, so just a quick summary. So we went over the governing equations, looked at some basic detonation models in the JWL equation estate. Then we went through and created our base mesh and cut out that building, created the face zones and the baffles and burst patches, set the charge, and then looked at some results. So that face zone and baffles, while we use it here for burst patches, it's exactly how you do basically any creation of burst patches, or sorry, not burst patches, baffles or anything like that within OpenFOAM as well. Yeah. So if you're interested, you want more help or anything like that, first recommendation is the user guide. I've tried to go through and put everything in there, whether it be equations or options. Has quite a few examples. This case is actually in there. We do training, both custom or private workshops. We haven't had a public one in a while. Bugs, submit them to our GitHub issues page, or if you ever want something new, you can always ask. I'm always looking for something new to do. So current and future work. So currently working on some immersed boundary with the work done in Foam Extend, primarily for projectile motion. We know interpolation based on we know ext, and then some additions to our true like Euler multi-phase, specifically for fluid. We have fluid solid right now, but fluid requires some additional work. References, and yeah, questions. Yes, let's see if I can figure this out. I am not sure how to let people talk. I saw a hand. If you just want to drop it in the questions, I'm not sure how to. All right. Well, I'll be here. If anyone has any questions, feel free to ask. Otherwise, thank you guys for coming.